So let's talk about discrete random variables, right? So this is really important. So we'll start with discrete random variables. So of course, now once we know what a random variable is, we'll now try to include the concept of probability to it, right? So probabilities are defined on events, which are essentially subsets of your sample space S. Okay. So when we say what do you mean by if you write P of a capital X is equal to small x? So what does this mean, right? So let's take the previous experiment that we have been doing. So this is the experiment in which we are selecting a ball from a bag at random, right? So you know the sample space is essentially these 8 elements because there are 8 balls. So 1, 2, 3, 4, 5, 6, 7, 8, and x is the weight of a ball selected at random, right? So that is how we define our random variable with capital X. Okay. So what does P of capital X is equal to 0.1 mean, right? So this capital X can take any values from the set which is small x, right? So if our capital X takes the value 0.1, right? So what does this mean? So when we write probability of X, capital X in fact is equal to 0.1, this means that the probability that either ball 1, ball 2 or ball 3 is selected, right? So when you say that, yeah, capital X, if it takes the value 0.1, that is 100 grams, or when you say that, yeah, the weight of a ball selected at random is 100 grams, so what is the probability of any such ball, right? So a probability of selecting any such ball. So this is essentially, you mean that out of all the possible 8 balls, you can select either ball 1, ball 2 or ball 3, because each of these 3 balls, they have the weight 100 grams, right? So let's say if you call the event E, if you define E as the event that either ball 1, ball 2 or ball 3 is selected, then your event is the set which consists of these 3 values, that is 1, 2, 3, right? And as you know, probabilities are defined on subsets of S. So this 1, 2, 3 is a subset of our sample space, which is defined here, right? So if we write, we can write P of capital X is equal to 0.1 is equal to P of E, which is the event that either ball 1, ball 2 or ball 3 is selected, because each of these balls have the weight 100 grams, right? So this is how we denote the probability, right? So this is the concept. Okay. So in fact, I'll also I'll try to include a few more examples here. So your sample space is all these 8 balls, 1, 2, 3, 4, 5, 6, 7, 8. Your capital X is essentially the weight of a ball selected at random, right? And X is essentially all possible values which capital X can take, right? So you should be pretty clear with these terminologies. So when you write X is equal to X, this means that, let's say in our case, if our X, if this takes a value 0.1, right? So we can write probability of capital X is equal to 0.1. So what does this mean? So we can in fact calculate this probability. So we know that the event E has 3 outcomes, 1, 2, 3, right? So there are 3 possible outcomes. The sample space has 8 possible outcomes. So this will be essentially N of E divided by N of S. So essentially 3 by 8, right? So there is 3 by 8 probability for this random variable to take the value 100 grams, right? So I hope, yeah, this makes sense. Okay. In fact, you can ask a lot of other questions. So for example, what will be probability of X is equal to 0.15, right? So you can define that as another event, E1, let's say E1. So that will be again this, and you know that there are only 2 balls which have the weights 150 grams. So those are essentially 4 and 5. So 2 by 8, that is 1 by 4. Or you can equivalently say that this 25% probability that our random variable capital X will take a value 150 grams. Can I get yes from you guys if you are able to understand this particular concept? The concept of probabilities, right? So our random variable can take all possible set of numerical values, right? Okay, perfect. So let's move ahead. So now, once we have introduced the concept of probability, so naturally arises another concept, which is what we also call as probability distribution function, or simply probability distribution. Okay, so yeah, just hang on. So uh, so the function, so this is a probability function of a random variable, because see, your random variable can take different values, right? So your x, capital X, in fact, in the previous example, it can take multiple values, right? So we define the probability function of our capital X. In fact, let's denote it first, and then we'll talk about how it is defined, right? So this is denoted as a small x, and then you write capital X, right? So this is equal to uh, P of capital X is equal to small x for each small x in the range of capital X. So this is how we define the probability function for this random variable capital X. Okay, so this is the notation uh, that we'll try to stick to, right? So this is denoted in this particular fashion. So remember, earlier we were writing only in terms of this particular notation, that yeah, P of X, capital X, is equal to 0.1. So that can be written in this particular notation as well, which is small f, small x, and then in bracket you have capital X. Okay, so in fact, a small x is so this is small x, and then this is the random variable, in fact. Okay, so it specifies how the total probability of 1 is divided up amongst the possible values of x, in fact, that is capital X, and it gives the probability distribution of x, right? So you know that your random variable capital X, it can take different multiple values. So from your sample space, if you associate a probability to any particular event or outcome, right? So if you're including all the events or all the outcomes in your sample space, so they will all add up to a probability of 1, and the probability distribution of capital X will tell you how this total probability of 1 is divided up amongst all the possible values of our capital X. So this is called as probability distribution. And in fact, probability functions, they're also called as probability distribution functions, right? So let me walk you through an example, and this notation will become much more clear, right? So first of all, there are two important properties, that this f of x is greater than 0 for all x in range of x, right? So this is greater than 0, and the summation of this fx is equal to 1, right? So let's try to verify these two properties and try to understand the probability distribution function for the context of the last example that we were discussing, right? So there we were discussing an experiment in which we have 8 balls in a bag, and we are selecting any particular ball at random, and we defined capital X as the weight of a ball selected at random. Okay, so f of x of 0.1, so fx of 0.1, let's read this as fx of 0.1 as probability that capital X is equal to 0.1, right? So this is defined as 3 by 8, right? Because there are 3 balls which this particular value, right? So remember, ne by ns, so this will be 3 by 8, right? So this is fx 0.1, and then let's say if you write fx of 0.15, so this is essentially probability of capital X is equal to 0.15, and this will be 2 by 8, which is again 1 by 4, and fx of 0.2 is equal to probability of capital X is equal to 0.2, and that will again be 3 by 8. Okay, so let's verify these two properties. So first property is that all the values of fx should be greater than 0, right? So in this case we can see that, yeah, this is greater than 0, this is again greater than 0, this is again greater than 0. So our first property is satisfied. The second property is that all these individual probabilities will add up to 1. Okay, so as you can see, 3 by 8 plus 3 by 8, so that is again 6 by 8, which is 3 by 4, and then plus 1 by 4, so that is again 1, right? So this property is again satisfied for this particular experiment, right? So this is what we can call as the probability distribution function of capital X, right? So this is defined as probability distribution function of X, right? So in fact, we can denote this in fact in another way. So in fact, yeah, okay, let me just go back. Okay, so in this case, so we can create a table, right? So we can create a table. So okay, so this is our capital X, and let's say this is our fx. Okay, so let's say if this x takes the value 0.1, 0.15, 0.2, so this probability is 3 by 8, this is 1 by 4, and then this is again 3 by 8, and if we sum up fx, so this will be 1, and each of these fx, right, so each of these values, so they are all greater than 0, right? So we have to our both the properties which are required for a distribution function, that is yeah, defined in this particular fashion. Okay, so a probability distribution is nothing but a way of specifying how so a way of specifying how our total probability of 1 can be divided into all the possible values of our random variable, that can possible values of a random variable. Okay, right? So Shruti is saying in range of capital X there could be certain for which probability of x is equal to 0. So shouldn't p of x is equal to x greater than equal to 0 for all x in range of x? So so in the case of, let's say, the experiment when we are tossing a coin, right? So our s is h comma t, right, and our x is the number of heads that we get when we toss a coin, and so this x can take these values 0 and 1. So probability of capital X is equal to 0. So this will be uh, what? So, and what probability of capital X is equal to 1, right? So can you guys tell me what will be the probability of these two? So maybe right, so this will be half and this will be half, right? So as you can see, this is nothing but fx 0 and this is fx 1, and in both cases we are seeing that your fx is greater than 0, right? So you need to yeah, be aware that uh, so in case of weights of students, can you check that certain x, see when you talk about those values for our random variable for which the probability is 0, so those are impossible events and will not take them into account. Okay, so okay, so I hope, yeah, that's clear, right? So this is important, so there is not equality here, it should be greater than 0, right? Of course uh, I can make a lot of constructs for which my probability will be 0, but do I actually need to bother about them? No, I don't think so, right? So all these individual effects should be greater than 0, right? So next, in fact, in continuation of this, I can show you some cool visualization. So suppose I select certain grids from here, right? So this is a grid of hexagons. Okay, so I'll select a few, right? So there could be n number of hexagons, and I'm selecting a portion of it, right? And I'll denote this that yeah, it will take a value, let's say 20, right? So I'll submit this. Okay, and now I'll select an other hexagons, right? So I can select other hexagons, right? So something like this, right? So okay, so now let's assign this a value of 1, right? So let's assign this a value of 30, right? So now we have reds, red hexagon, purple hexagons, and then of course there are white hexagons, right? So now what we'll try to do, we'll try to sample a distribution for this particular random variable, right? So so in this case, let's sample the distribution. So essentially all these dots, they can appear randomly and in any particular hexagon. Okay, so here as you can see, the probability of a dot appearing in these red hexagons is 0.21. For them appearing in the purple hexagon is 0.1, and then they appearing in the white hexagons, that is 0.59. So of course, as we sample it more, so this is going to change a bit slightly, and as you can see, all these three probabilities, they will add up to they will all add up to 1. Okay, so this is the probability distribution, essentially very similar to how we discussed in this particular example, right? So it's pretty similar to that only, right? So probability that yeah, x is equal to 0, so it's 0.59. Probability of x is equal to 20, that is 0.21. Then probability of x is equal to 30, this is 0.21, and if you add them together, so this will be 1. Okay, so you can experiment with this, and yeah, get yourself more exposure to the understanding of the probability distribution, right? So in this case, how can we write the probability distribution? So in this case also we can yeah, make a simple table, right? So x is essentially, it takes value 0, 20, 30. This is what I just came up with. Of course, you can write anything what you want. And then this is of course the f of x. So this right. So this is kept right. So this is in our case this was 0.58. Sorry. So this is 0.58, and then let's see. So so 0.58, 0.22, and 0.20, right? So if you add them up, so 0.58, 0.22, 0.20. So this is your 80. 80 plus 20 is 1, right? So our second property is satisfied, and each of these are greater than 0. So our individual probabilities are greater than 0, so we are satisfying both the properties of this probability distribution function. So I hope yeah, this particular concept is clear, right? So let's move ahead. So I hope you guys are with me at this particular point of time, right? So yeah, please do let me know over the chat whether you are able to understand probability distribution function. So remember, this is an example of what we call as discrete probability distribution, because our random variable is discrete. Okay, because it can only take 3 possible values here: 0.1, that is 100 grams, 150 grams, and then 200 grams, right? So there are 3 possible values, right? Okay, so let's move forward. So now let's talk about cumulative distribution function, right? So this is again really important. So the cumulative distribution function, CDF, of x is capital F, capital X of x, small x, is equal to, is defined as probability of capital X less than equal to small x, right? So earlier when we defined small f, right? So when we, right, so I'll just tell you what's the basic difference between the two. So we wrote something like this, right? And we defined this as probability of capital X taking this value small x. But when we write in this manner, right, so we mean probability of capital X less than equal to small x. So this is your simple probability distribution function, right? And this is what we'll call as cumulative, right? So I think some people might have already been able to guess why we are calling this cumulative probability distribution, right? So this is okay. So in this case, so our cumulative distribution function or cumulative probability distribution function is defined. So whenever someone skips the word probability and they say distribution, so you should assume that they're talking about a probability distribution. So when I say let's talk about this particular distribution of this random variable capital X, so you should assume by default that I'm talking about a probability distribution of that random variable capital X. Okay. So what is the meaning of writing this? That is probability of capital X less than equal to x, small x, right? So it gives the probability that x assumes a value that does not exceed x, right? So this is an important phrase, does not exceed, because I have less than equal to sign here. That means all the possible values which I'm not considering here is greater than x, right? So that's why a certain does not exceed x. It can be equal to x, but it does not exceed x, right? So this cumulative distribution function of x, it gives the probability that x assumes a value that does not exceed small x, right? So CDFs are also known as distribution functions, right? So they're also known as DFs. Okay. So here probability distribution functions, they're also called as probability probability distribution or probability distribution functions. In fact, CDFs, they are called distribution functions or DF. Okay, so a bit of confusing terminology, but I think you guys will be able to comprehend this, right? So CDFs are also known as distribution functions, and then you can simply call this as probability distribution of x. Okay, or we can simply call it probability function. Okay, so so in this case we again have that same experiment. We have 8 balls, and all these balls have certain weights. So our random variable capital X is the weight of a ball selected at random. So capital F of x is of 0 is probability of x less than equal to 0, and this will be equal to 0, right? F of capital X is 0.1 is the probability of capital X less than equal to 0.1. So this is probability of x is equal to 0.1, right? Because there is no other smaller value than 0.1, right? This is 0 because there is no ball with 0 weight, right? And then here if you write probability of x less than equal to 0.1, so there's only one value which is less than equal to 0.1, that is 0.1 itself, right? So the probability of that is 3/8. When you write fx 0.15, that means probability of x less than equal to 0.15. So when I say if x less than equal to 0.15, so what sort of probabilities I'll take into consideration? So of course 0.15, because equality sign is here, and then also 0.1, right? Because this particular value is less than equal to 0.15. So probability of x is equal to 0.1 plus probability of x is equal to 0.15, right? So this is how we add these two probabilities when I'm calculating this particular cumulative probability, right? And this will be again, so probability of x is equal to 1 is 3/8, and probability of x is equal to 0.15 is 2 by 8, which is 1 by 4, and that will give us 5 by 8. Okay. And if we talk about fx of 0.12, so this is probability of capital X less than equal to 0.2. And what are the sort of possible values which are less than 0.2? So this is x is equal to 1.1, x is equal to 0.15, and then capital X is equal to 0.12. And what are the individual probabilities for these? So we'll just add them up. So in this case for 0.1, this is 3 by 8, then 2 by 8, then 3 by 8 for 0.2, and they all add up to 1. I have a nice visualization for you guys, right? So this is how I defined my function, right? So this is my capital F of X, right? So let's write this. How do we write that? Okay, so I'm talking about the CDF, which is the cumulative distribution function. So this is X, and if we were to write, right, so in this case, right, so this will take a value 0 if X is between 0 and 0.1, right? So something like this, right? And then similarly we'll write it will take a value 3 by 8, right? If the X is equal to 0.1 less than 0.15, and then we'll write 1 by 4. Okay, just hang on a second. So if X is between 0.15, okay, so 0.15 less than, so X less than 0.1, greater than 0.15 but less than 0.2. So for this our probability is 5 by 8, and if X is greater than 0.2, so this will be 1. Okay, so now yeah, you guys will be able to see this, right? So this is what I have written the function, right? So if the ball's weight is between these two values, so this will be 0 because there is no such ball. If it's between 0.1, here I have the equality sign, but here I do not have, so 0.15. So this is the probability will be, in fact, the cumulative probability will be 3 by 8. If I have 0.15 less than equal to X less than 0.2, so this will have the probability 5 by 8, right? And if we talk about X greater than equal to 0.2, so this will be 1. Okay, so I hope, yeah, this makes sense. Okay, so in this case I'll just, yeah, in fact, so here as you can see, in fact I'll just, right, so here if our value is between 0 and 0.1, right, so the CDF or the cumulative probability is our 0. If it's between 0 and so if it's between 0 and 0.1 and 0.15, so this is 3 by 8, so which essentially is close to 0.4. And then if the value is between 0.15 and 0.2, so the CDF probability will be 5 by 8, right? And then if the X is taking a value 0.2, right? So remember, this is 0.2, right? So it's taking the value 1 for all the values greater than 0.2, right? So in this case, it's taking only discrete values, right? So there are steps here, right? So this discrete cumulative distribution function is an example of a step function for this particular experiment, right? So this particular discrete CDF is an example of step function, right? So as you can see, right, so if your X is between these two values, that is 0.15 and 0.2, and if you write a probability of X, let's say between 0.15 and 0.2, right, so there right, so you will be taking so if any X lies between 0.5 and 0.2, so our cumulative probability will be defined by capital X less than equal to that particular value. So it can be, let's say, 0.17, So our capital X is less than 0.17. That means we'll include all the balls which have 100 grams weight and also 150 grams weight, right? So that's why we have 5 by 8, because there are 3 balls with 100 grams and 2 balls with 150 grams out of the 8 balls, right? So this is the example of CDF. Okay. So nice properties, right? So as you can see, so in this case, fx of 0.2 is 1, right? So this total, the cumulative probability is 1. So let's say uh, if you pick any ball whose weight is, so if you try to find, let's say x takes the value 1.5, right? So the cumulative probability will be defined by probability of capital X less than equal to 1.5. So all the balls are less than 1.5 kgs, right? Their weights are less than 1.5 kgs. So that's why the probability for that random variable to take that value less than equal to that will be 1, right? So the cumulative probability is going to be 1, right? So this is the example of discrete CDF.